Hey guys, so let's just put my laptop on the bed. We'll quickly do one part of the two part. Right, so I feel all the laptop on my ear. Alright, we're putting this picture as boxes. Start lettering space.
It's RAM number 6, boy 81. It's on the board here as well. Okay. So it's on the board there. RAM 6, boy 81 altogether. Okay, so today we're going to see recursion and abstract data types. I know that recursion you've seen before in Introduction to Algorithms. We will talk about it again and make the link with systems architecture and move on from there. Okay, so talking about recursive algorithms and an introduction to abstract data types, which you haven't seen before or not here. Okay, so here I'm coming to, I apologize if I sound a bit croaky. If I say something that you don't quite get it, interrupt me. So I wasn't well yesterday and the day before, and I've been lecturing all morning today. So if I don't make sense, tell me, okay? And we can revisit, try to describe things or discuss things better or in a different way. So we are looking at recursion. And in order to look within recursion, I'm going to motivate it a bit. So why do we need recursion? So when we have very complex concepts or algorithms to solve, we always try to break them up into smaller concepts, and even with tasks that you have to do for your own time management. We always break things down into smaller, more manageable chunks, and then as a whole, then bring them all together to make sense as a whole to achieve what we want to do. So the same thing applies for algorithms. We break problems down into smaller chunks. In recursion, we use this approach, and it's not the only place in algorithms where we use this approach of divide and conquer, but in recursion, we use this approach. We think of the simplest possible way of solving a problem, and then we say, okay, if that solves that little bit, what do I need to add to have it being able to treat the whole, right? So how do I deal with the rest so that incrementally those combined together and give me a solution for the bigger problem. So if we're talking about, so not all problems are amenable to recursion, okay? But for the problems that are amenable to recursion, we have to look for the simplest possible case for that problem to be solved. So what's the simplest input ever that we could have in order to be able to answer that question? And then we think how it relates to having a larger or more complex task to solve, or this input size to solve. So if the input is simple, in order to analyze in terms of time and space complexity, if the input is simple, then we figure out how long does it take. If we're talking about the more complex case, then we have to see, well, how many times will I call this particular algorithm, and how long does it take to execute it each time? So if for each time that we call it, we had a loop, for example, and we call it, so a loop that executes in order n time, and we have n recursive calls, what would be the time complexity for such algorithm? So a recursive algorithm that is calling itself n times, and within each of the calls we have a loop that is order n to execute. N squared, exactly. So the time complexity there would be n squared. If what we're calling it takes is constant, so order 1, and we have order n calls, then the time complexity there would be order n. Now, so that's for time complexity. In terms of memory complexity, what is your gut instinct? What does it tell you about recursion and space or memory complexity? Okay, so we will get there by looking at examples and have you think about it, okay? So I didn't expect you to have an answer ready in your tongue, so don't be disappointed. Okay, so you've seen recursion before, and so it was introduced to you in your Introduction to Algorithms module, and we are continuing with that. So again, we find the simplest case, we think of the simplest case possible first, and then we think of how we step it up, how we combine it with the other inputs in order to solve the larger problem. If you're familiar with proof by induction, it's almost like the reverse approach to proof by induction. So here's an example, factorial. So if you remember from your maths way back when, factorial, and factorial is n times n minus 1 times n minus 2 times n minus 3, and so on and so forth, until we get to the number 1, okay? So that's what n factorial means. So that's the definition here. Now, the base case, so the simplest case possible for solving n factorial is if Rn was the number 0, right? So factorial of 0, we know by definition is 1, okay? So that's when we get to 0 or to 1, we can't stop, right? And then the result of n factorial for anything else is the same as n times the n minus 1 factorial. So 3 factorial is the same thing as 3 times 2 factorial. 100 factorial is the same thing as 100 times 99 factorial, and so on. So our base case is when Rn is 0, we know that it should return 1. As 100 and introduced to you. So if you remember from your maths way back when, we combine it with the other input in order to solve the larger problem. if you're familiar with proof by induction, it's almost like the reverse approach to proof by induction. So here's an example, factorial. So if you remember from your maths way back when, factorial, n factorial is n times n minus 1 times n minus 2 times n minus 3, and so on and so forth, until we get to the number 1, okay? So that's what n factorial means. So that's the definition here. Now, the base case, so the simplest case possible for solving n factorial is if our n was the number 0, right? So factorial of 0, we know by definition is 1, okay? So that's when we get to 0 or to 1, we can't stop, right? And then the result of n factorial for anything else is the same as n times the n minus 1 factorial. So 3 factorial is the same thing as 3 times 2 factorial. 100 factorial is the same thing as 100 times 99 factorial, and so on. So our base case is when our n is 0, we know that it should return 1, okay? So that's the base case. And for all other situations, factorial should return the number we've given it as input times factorial of that number minus 1. Yeah? Clearly seen here. This is echoing. Seen here from that definition here, from the formula definition there. Fine. So in terms of actually implementing this, here is a simple function that does solve that problem. So if n equals 0, then we return 1. This is this case, right? The base case. If it's not equal 0, then it's this case that we have to implement. It's n times n minus 1. So we say that we can use an auxiliary function, an auxiliary variable. We don't have to, but we can use an auxiliary variable and say we give to that auxiliary variable the value of factorial of n minus 1, and then we return n times that value. So it's n times factorial of n minus 1, which is exactly what was written here. Yes? Agreed? Questions there? Cool. Okay. Let's move on. I have added here these numbers, 0, 1, 2, 3, 4, are just the line numbers of these statements here in this particular function, just so we can refer to them in the next slides. So we will see. So what is really going on when we call factorial in terms of what's happening within the operating system, okay? So what's going on here? What happens, systems architecture, what happens when we call factorial, so that function, with some input value? Well, a frame is created in memory, yeah? A frame is created in memory in which we will have spaces for the local variables that are being defined, so memory spaces for these local variables, and we will know in exactly which line of the program that we are executing. Okay, so when we first call it, we call it with the value that is given to the parameter that we were passed on. So we call factorial with the value 2. This is this variable n. It takes the value 2. Auxiliary, there is aux is a local variable that is not yet defined the value for. And we start by executing the first line. So in the first line, it asks us here, if n equals 0, is n equals 0? No. So then we don't do the n, we go to the else. Then it says, okay, when we get here, it says we need to assign to this auxiliary variable the value of factorial to of n minus 1. So what happens here? As soon as they see this, or the operating system sees this factorial of n minus 1, it's another call to factorial. So what happens then? We have, so that's where we are now, that line. We need a value for this auxiliary variable. The operating system creates another frame for the same function name, but it's another frame. And it stacks it on top of the other frame that we were executing. And this is the one that we'll be executing now. And in here, we start again with the same information. What's the value for the parameter? The value for the parameter here is 1, because n had the value of 2, right? So n minus 1 is 1. So we call factorial here with the value of 1. So that value is assigned here in the space that is needed in memory. The value for the auxiliary variable here is not yet defined. And we start executing on the first line of the code. And if n equals 0, which it isn't, we go to the else. Again, auxiliary variable is going to get the value of factorial of n minus 1. n is 1, so now n minus 1 is 0. What does the operating system do? It calls factorial again, but this time with the parameter 0. So what happens? The stack continues as it was, yet another frame is created for this next call to factorial. n being 0 now, because that's the value that it was passed when it was called from here. n is 0, and we start executing from the first line of the code. We don't have a value for auxiliary yet. Now we check if n equals 0. Well, n is equals 0, so return 1. So that's what's going to happen. This call will return 1. It will go away from the stack, and the value 1 will be assigned to auxiliary, because that's what was happening with the return of that call. It was being assigned to auxiliary. Okay? So this is what's happening in memory, in the actual computer, as we are executing a function call. Okay? You do remember that, right? Cool. Fine. So that's what's happening here. So now we have this returning 1. It returns 1 there. That particular top frame goes away. It's used for something else. That bit of memory is released. And we can continue here. So we have now that auxiliary is 1, and we have to return. So next line of code to execute here is this one. We have to return n times the value in auxiliary. So it's 1 times 1. We return 1. So this frame will go away. And this auxiliary will get the return value of this call, which will be 1. So that's what happens. So the value of 1 is placed there, and that frame goes away. So that bit of memory is released. So then we are here. Remember, this was the line of code we were executing, so we continue there. So auxiliary got 1, so now we have to return n times auxiliary. So 2 times 1, we return 2. And that's what happens. Okay, so this is what happens in the operating system and in memory. So what the operating system does with the computer's memory as we are executing these function calls. It is as if it was any other function call. It creates a new frame for whichever function is being called, with space to change values of local variables, and executes them. Once that particular call is done, its result is returned, and that space in memory is released. Okay? Yes? No questions? Clear? Oh, clear. That's good. Cool. So that's what happens. So with that, as you can see, we're creating frames for each of the calls. Yeah? We are creating different frames for each of the calls, and this is taking space in memory. Ta-da! Memory complexity, right? Space complexity. That's what we need to consider when we are looking at recursion, is how many recursive calls we have. Because for each recursive call, we create a new frame in memory. So that's taking memory space. Okay? Yes? Good. All right. This is all what was going on as we were doing this. So this is the call stack, yes? You've heard of it with that thing, yes? No? Thank you. So that's what's happening. So it doesn't have really a copy of the whole code that I was showing in the previous slide. All it knows is which line it's executing. So it keeps track of what's the next line to execute when it returns from the call. So that's what's really kept into the stack, maintained in the stack. Okay. So when we were talking about that example of factorial, what are the time and space complexity here? So well, we can look at it even here. So what's the time complexity of factorial as depicted here? Time complexity of executing this particular function. Log n. Why do you think so? Not correct.
O(n)?
O(n). Why?
Because actually we need to have as many steps as this n.
We call this as many times as n. Why? We start with the input being n, and then we're always calling it with n minus 1. So n minus 1, n minus 1, n minus 1 is as if we were iterating on an array, guys. We start from the first position, and plus 1, plus 1, plus 1. Here it's doing the same type of thing. It's calling itself. So this factorial is being called n times. So it calls, we call it with n, and that is n, then with n minus 1, and then n minus 1, and then n minus 1 until we get to 0. So this function calls itself n times. And when we are executing, there are no loops in here. Yeah, it's all O1, what is written in there without the recursive call. Everything else is constant. Yeah, so we call it n times, and when it executes each of these calls, takes a constant amount of time. So then the overall time complexity is O(n). Do you see this? Okay, all right. And how about space complexity? So what's going on with memory here? Yes, I heard from two different people saying, yes, it is the same thing as with the time complexity. Why? Because each recursive call creates another frame in memory. How many variables, how much information are we needing to store in each of those recursive calls? It's only these guys, it's only these variables, yeah? So it's constant number of variables that we need to store for each of the frames, and the number of the frames is the number of recursive calls. If we're calling factorial n times, we will have n frames. And n times O1, which is the constant amount of memory that is being required for each of the frames, it is O(n) as well. Questions? I will be really happily surprised if everybody understands it the first time I explain, okay? So I hope you do, but if you don't, ask, all right? This is something that year on year, I see people struggling with. So here's another example. So don't feel bad if you don't get it at first, it's fine. Here's another example, a function called power. So calculating x to the power of n. X to the power of 0, we know equals 1. So that's our base case. And x to the power of n for all other n's that are greater than 0, and integers, is the same thing as doing x times x to the power of n minus 1. So x squared is the same thing as x times x cubed is the same thing as x times x squared, x to the power of 4 is the same thing as x times x cubed, and so on and so forth. Yes, do we all remember that? And squared to the power of n minus 1. So x squared is the same thing as x times x cubed is the same thing as x times x squared, x to the power of 4 is the same thing as x times x cubed, and so on and so forth. Yes, do we all remember that? And so we have here so that are greater than 0, x to the power of 0, we know equals, here's another example, a function called power. So calculating x to the power of n. X to the power of 0, we know equals 1. So that's our base case. And x to the power of n for all other n's that are greater than 0, and integers, is the same thing as doing x times x to the power of n minus 1. So x squared is the same thing as x times x cubed is the same thing as x times x squared, x to the power of 4 is the same thing as x times x cubed, and times x integers is the same thing as doing x times x to the power of n minus 1. So x squared is the same thing as x times x cubed is the same thing as x times x squared. X to the power of 4 is the same thing as x times x cubed, and so on and so forth. Yes, do we all remember that? And so we have here a base case, and how we build on that base case for more complex, or in this case, for bigger numbers, okay? So here's a definition of a function to actually solve that problem. So we have here the base and here the exponent being passed as parameters. So if n equals 0, we return 1. This is this base case here. So every time we are creating a recursive as parameters to actually solve that problem. So we have here the base and here the exponent being passed as parameters. So if n equals 0, we return 1. This is this base case here. So every time we are creating a recursive algorithm we have to think, what's the base case, right? And we define what that is, and we define how the more complex case relates to or built upon the base case with a recursive call for it. So we always have to have, it always has to have an if. If it is the base case, we do the thing that's in the base case. If not, then we do the other thing, the other bit that we defined as helping us solve the problem. So in this case, if n equals 0, which is the exponent being 0 in this case, then we know we have to return 1, regardless of what the base here, the x is. And if it is not, if the exponent is not 0, then we return x times power of x minus 1, x times x to the power of n minus 1. It's the same thing, okay? So it is doing away with that auxiliary variable that I had on the previous example when I said we didn't really need it. Well, here we're not even using it because we don't need it, okay? Yes?
Why don't you just use power xn rather than x times power xn?
So power xn is how this is called to start with. And then we check. If the exponent is not 0, then it's this thing here. So if the exponent is not 0, how can I make it to be able to solve? How can we try to solve this equation? By reducing the exponent that we're dealing with, such that eventually my exponent will get to 0. So if I say x to the power of n is the same thing as x to the power of n, yes, it is, but it's not helping me move closer to the solution. Now, if I want to solve the x to the power of n by reducing the exponent, making it easier to figure out this bit with the exponent, then I have to make it smaller. And so that's why I have x times x to the power of n minus 1. Yes?
Going back a few slides, when you said stack, well, like, what do you mean by that?
Yeah. Okay, so this is the call stack. So this is what happens. So this is systems architecture. This is what happens in the computer. So this is what the operating system does as we are calling functions. So we call a function. What does the operating system do? It creates a frame, is the name. It creates like a block in memory. It creates a frame in the call stack, which is a term that we use to define where this part of the memory is separated to control, to deal with function calls, with things executing. So it creates a frame for that function call with space for the variables that are needed by that particular function to execute, and giving it the parameters that it needs to start executing. And then it runs one line at a time. So it runs one line at a time, and it increases the program counter to know, okay, I finished this line, let's go to the next, so find the next one in memory, and changes the values in these variables that it's doing so, okay, depending on what those statements in the program are telling it to do. So the stack is the name that is given. So the call stack is the name that is given to the place in memory where this information is kept by the operating system. And every time you have a new function call, it's a new frame that is created on top. On top is a figure of speech, right? Somewhere in memory that we're saying it's on top because you cannot get to the lower one until you're finished with the one that was on top. So you finish the one that is on top, you get rid of it, and then you're able to get back to the ones below, okay? Any other questions? Yes?
What's the line mean?
It's the program counter. It's what is the next line of code to be executed in that function. Any other questions?
Let's say line 3, by the way. No, sorry, line.
Yes, I'm showing you why it says line 3. So when we were executing, so let's start. So when we started executing here, this started from the first line of code, so line 0. We checked is n equals 0, no. So then it went straight into the else, which is in line 2. Then line 3, there is a recursive call here. So when it is in line 3, we have the call for the other factorial, so we have the creation of the new frame on the stack. And so it has to remember that it was in line 3, to know where to continue from. So the operating system. And so when it is in line 3, we have the call for the other factorial, so we have the creation of the new frame on the stack. And so it has to remember that it was in line 3, to know where to continue from. So the operating system needs to know where to continue executing from once it comes back from that call. Okay? More questions? Okay. So we were doing a similar thing with that power. So in here, we are using the same approach to solve the problem of a number to some power elevated to some other integer in order to give us a value. So we are using recursion to do it. We have a base case for when the exponent is 0, we return 1. Otherwise, we return that number times the power of that number elevated to the original exponent minus 1, okay, which was this step function defined for the recursive function. Yeah? Okay, so if we are looking at power, it will execute the exact same way. What are time and space complexities here? So what is the time complexity for this function power here? Why do you think so? So the suggestion was O(n) squared. Why? Just guess. What are time and space complexities here? So what is the time complexity for this function power here? Why do you think so? So the suggestion was O(n) squared. Why? Just guess. Okay, that's not good enough. You were trying. O(n), yeah. It's O(n). Why is it O(n)? It calls itself n times. The step function, all it's doing is we're reducing it by 1. And so with it, there are no loops in here, nothing like that. So every time each of these statements is executed only once. So this particular call will be constant. And how many calls do we have? We have n calls, because we start with n and then n minus 1, minus 1, minus 1, minus 1 until we get to 0. So it is that we have n recursive calls, and for each of these calls, it is a constant time complexity. So then the overall time complexity is O(n). Yes? Okay, how about space complexity here? Same thing, O(n) again. And why? Yeah, so I couldn't tell who was speaking. I had one answer from here and one answer from there. Cool. and it is because we have to create n frames in memory because it's calling itself n number of times, and all we have is that we don't even have any local variables here. All we need to keep track of are the values of n and x on the stack, okay? Cool. Easy? if you get your head around the fact that all we're doing is talking about the call stack, so it's how many times we have these recursive calls, then it's fine, then it's easy, okay? So don't let the looks of anything ever make you worry needlessly. Okay, so now to...
I just get a right case. So I've got to get ready for university. Train at 3:15. So I'm going to do maybe another 5 minutes. Some lunch and get out. And I'll continue tonight. See what I'm doing tonight. Yep, I'll be back online.
A definition of another term. So recursion, you already knew what it was. Now we have explicitly seen the link with what's happening in the operating system. So what's happening in the machine, what the operating system is doing to execute a recursive function.
Wait, this Java is to C++. How would I, if I'm wrong, then I'll leave a comment. I think it's Java.
Function in order to understand its time and space complexity. Now the definition of tail recursion. A function is tail recursive when the last thing it does is to call itself. Okay, so the last thing it does is call itself. So in this particular case, we have if something, blah, blah, right? Then if I is greater than 0, we print that I, and then we call tail of I minus 1. And that's the end of it. So the last thing that is being executed is the call to itself. It's the recursive call, okay? So that's a tail recursive function. So the last thing it does is a call to itself. Why does it matter? Why do we care about defining this term, tail recursive? It's because when we have a function that is tail recursive, we can very easily change it into non-recursive. So make it solve the same problem using a loop. It's very easy to go from that to this. Why might we want to change something from being recursive to being iterative, to having a loop? Less space, yeah, that's it, less space, okay? Does it make a difference there in terms of time complexity? No, so no change in time complexity, but less space consumed. Why would we ever want to use recursion then? It looks nice, it's elegant, yeah, it's very elegant. And with recursion, it's much easier to prove correctness, okay? So if you need to prove, actually mathematical proof, right? It's not show by means of example, no, mathematical proof. So if you need to prove that something is correct, then recursion is more amenable to this sort of proofs, okay? So those are reasons why we might want to use recursion. So here's another example of a tail recursive algorithm, and we are transforming Factorial into a version that is tail recursive. So we're using this auxiliary function in which we call fact. This fact is tail recursive. So this is dealing with, it's calling fact with the value that we were asked to do Factorial for and the value 1. So 1 is accumulating the product so far, and we do the n minus 1, n minus 1, n minus 1 here. Okay, so this is a way of transforming the original Factorial that we saw into a tail recursive Factorial. So why am I saying that this one is tail recursive? It calls itself at the end. Now, a question that I get asked every year, so that's why I'm asking you here. How about this n times product? I get asked, isn't that the last thing that is being done? Is it the last thing that is being done? No, we need to calculate this n times product in order to make this call. So this is solved. So the n minus 1 and n times product, they get executed by the operating system before the call to fact. So the last thing that is being done is the call to fact. That's why I can say that this one is tail recursive, because that's the last thing. So this is solved. So the n minus 1 and n times product, they get executed by the operating system. Isn't that the last thing that is being done? So n minus version. Actually, less space. Yeah, that's it. Less space. Okay. Does it make a difference there in terms of time complexity? No. So no change in time complexity, but less space consumed. Why would we ever want to use recursion then? It looks nice. It's elegant. Yeah, it's very elegant.
One sec. Hello?
And with recursion, it's much easier to prove correctness. Okay, so if you need to prove, actually mathematical proof, right? It's not show by means of example, no, mathematical proof. So if you need to prove that something is correct, then recursion is more amenable to this sort of proofs. Okay, so those are reasons why we might want to use recursion. So here's another example of a tail recursive algorithm, and we are transforming Factorial into a version that is tail recursive. So we're using this auxiliary function in which we call fact. This fact is tail recursive. So this is dealing with, it's calling fact with the value that we were asked to do the Factorial for and the value 1. So 1 is accumulating the product so far, and we do the n minus 1, n minus 1, n minus 1 here. Okay, so this is a way of transforming the original Factorial that we saw into a tail recursive Factorial. So why am I saying that this one is tail recursive? It calls itself at the end. Now, a question that I get asked every year, so that's why I'm asking you here. How about this n times product? I get asked, isn't that the last thing that is being done? Is it the last thing that is being done? No, we need to calculate this n times product in order to make this call. So this is solved. So the n minus 1 and n times product, they get executed by the operating system before the call to fact. So the last thing that is being done is the call to fact. That's why I can say that this one is tail recursive, because that's the last thing that is being executed, okay? Not the n times product. This is just an argument that will get resolved. So this needs to be performed before we make the call. Okay, so once we have that.
Radios. Time to go. Probably looking around 9 or 10 o'clock. So, yeah. Let's end this.